Welcome to an example we have here. It says the amount of pollutants that are found in waterways near large cities is normally distributed with mean 9.5 parts per million, ppm, parts per million. So there's 9.5 parts of pollutant per million overall parts of water, and standard deviation 1.5 parts per million. Okay, so there's a little bit of pollutant. That's the average amount of pollutant in the water, but there's some deviation, some difference from the average in the waterways leading to a city. They're checking different waterways leading to a large city. 37 randomly selected large cities are studied. So how do they do this? They keep stats on this kind of stuff to make sure our water's pure. It's stats is used here too. So 37 randomly selected large cities are studied. Round the answers, blah, blah, blah. First off, what is the distribution of X, capital X, and then down here, X bar? That's a little weird. Let me explain what's going on there to you. So capital X equals for one city, whereas X bar, put it over here, X bar. So whenever you have that bar above the X like that, here, let me do a better job there. That always means the average for several cities. So whenever there's a bar above, like this bar right there, that means the average for several cities. So you do want to know that in stats. That bar means average, mean. So it's the average for lots of cities. So whenever they're talking about just X, just capital X, regular X, that means just like for one city. When they're talking about X bar, they're talking about, well, what if we did like lots of cities? In fact, they said 37 in this case. All right, so here we go. So what are we gonna do? Well, you know how it works, right? This is always mean and standard deviation, right? You know, because they just want you to say, what's the distribution? Well, it's it's a normal distribution. It could be a bell curve. The mean, well, it says right there, mean is 9.5, and the standard deviation is 1.5 parts per million. Okay, great. Now, here's the part that's going to be a little tricky. You might say, well, it's just the same thing again. This is done. Well, kind of. Let me show you. Normal distribution again. The mean is still just the same. But here comes the tricky part. See this different number here? How did they get that number? What did they do? Well, they, I'll write it right here. Standard deviation is going to be, um, standard deviation. Well, here, let's just say you have to divide by the square root of n, where n equals 37 cities. Yeah, so this is going to be, that's going to go right here, is 1.5. We take the standard deviation, 1.5, which is, right there, divided by the square root of 37. And when you hit equals on your calculator, you're going to get 0.2466. That's how they got that number. They took 1 point, they took they took the standard deviation, they divided by the square root of it. Now, why? What's that all about? Well, this isn't really the time to explain it all, but just generally speaking, when you talk about a group average, which is what X bar, so this is X, the second one is X bar, it's average for a group, and the first one was just X, one city. If you're talking about a group of cities, then for a group of cities, grabbing a group of cities, you're going to have less variation. It's going to change the standard deviation. I'll talk more about that in class, explain a little bit more. So that's what's going on there. It's going to be 1.5 divided by the square root of 37. So it's 0.2466. So because we're talking about a group, not just one city at a time. So that's how they get that. Okay, so let's come on down now. What is the probability that one randomly selected city's waterways will have less than 10.3 parts per million? Now, notice, I want you to see, I'm going to try to keep the color coding consistent. It's a lot of C's there. Color coding consistent. This says one randomly selected city. And then the next one is going to say for the 37 cities, less than 10.3. See how they're both saying less than 10.3. But for part C, it's one city. For part D, it's 37 cities, the average for the 37. That's the whole point now of this chapter is we're going to take what we learned in the last chapter, chapter 6, and now in chapter 7, we're doing the same thing, but we're doing it for groups. And we're going to do both things. All right, so how do we do it? So first off, let's come on down and let's do part C right here first off. So part C. You already know how to do this problem. We just draw a bell curve. You know the drill, right? Draw our bell. Put the mean in the middle. What's the mean? 9.5. So the average, for the cities, the average pollutants, 9.5 parts per million. So okay. So what's it say? Less than right up here, less than 10.3. Where's 10.3? Well, 10.3 is, a little bigger than 9.5. So I don't know how far that way. And they say less than. Where's less? Less goes this way, right? Less than. So we're talking about that part of the taco, that part of the bell curve, right? We want if we're saying, so here's how the pollutants spread out for the waterways near large cities, right? Um, so for the average city, I'm sorry, for on average, the it's 9.5 parts per million, but some cities have more, some cities have less. So we're saying, what's the probability if you grab one city, one randomly selected city? If you have one city at random, what's the chance it'll have? And we say, okay, how about Fresno, or how about Lemoore, or how about whatever? Then it's going to be 10.3 parts per million or less. Well, probably it's going to be that's more than half the taco. That's more than half the bell curve, isn't it? So more than half of the cities are going to be 10.3 or less. Okay, so anyway, so how do we find it? We go to the calculator. We've got to say, well, here's the low. The low is negative 6 nines. The high is right here, 10.3. We want to know the P, probability. Let's go. I'll just show you real quick on the calculator. Let's do that. We'll get on to the other parts here. All right, let's go there. Get that out of the way. Oh, let me get the notes open also real quick here for us. All right. So there it is. So in the notes, I'm right here. I'm on, so unit 2 notes, right? Unit 2 notes. Come on down to number 5, norm distributed. We're talking about first draw the bell curve, put stuff on the graph, use the online norm probability calculator. Okay, so we're coming back here. So here's the online calculator. Here's click on that, the online calculator right there. It opens up with this right here. Go to the normal probability calculator. Click on that, number 8. Okay, so it's the low, negative 6 nines. The high is what? 10.3? Yeah, 10.3. 10.3. Right. And the mean, what is the mean? 9.5. Standard deviation, 1.5 from city to city. It varies a little bit. All right, calculate. There's the P, 0.7031. That's the exact answer they got. Same-o, same-o, same-o. So there we go. Let's go back and see it. Okay, so right here, see, we got their answer, 7031. Yep, that's the chance. In other words, this is 0.7031. So 70%. Basically, this looks like more than, it's definitely more than half. This is 70% of the bell curve. 70% of the cities are going to have 10.3 parts per million or less. So for example, let's make this real for you. What if what if that's the safety zone? What if we say, okay, for the cities in California, we found that the average city has 9.5 parts per million pollutants with a little bit of deviation, some more, some less. Average deviation, standard deviation, 1.5. Okay. So well, if that's the case, if I was to grab, and we're saying, 10.3, as long as you're 10.3 or lower, let's say, it's safe. It's considered safe by health standards. So if that's the case, then if I, what percentage of all the cities, or if I was to grab one city at random, what's the chance it would have 10.3 or less, that it would be safe? Well, that's going to be more than half of the cities, right? Because half of them are 9.5. So this is 10.3 or less. Well, it turns out 70% of the cities. There'd be a 70% chance if you're going to grab a city at random, because 70% of the cities have 10.3 or less. Okay, that's great. Now, part D. It's almost the same question. Still, it's less than 10.3. I mean, how's that any different? That's the new part I want to make clear for you. Let's do it. Okay, so come in here. I'm going to draw. Well, you know what? I don't even need a new one. Yeah, forget it. I mean, it's going to be the same, except for one tiny, teensy tiny thing. It's going to be the same. It's the same graph, right? I mean, it's the same bell curve. We're saying 10.3 or less, right? The middle's still 9.5. It's all the same. What's the difference? The difference is now you're saying, what's the chance if I grab 37 cities at random, not one city, like boom, Los Angeles, or boom, San Francisco. I'm grabbing 37 cities and asking about the average for 37 cities. So that's quite a different thing. You're grabbing 37 cities all at once, right? So Los Angeles, San Francisco, Fresno, Lemoore, you know, Sacramento, on and on and on and on and on you go. 37 cities at random, and then take the average amount of pollutants for those 37 cities. What's the chance that average of those 37 will come out less than 10.3? That's what X bar is all about. The average of a group rather than just one city at a time. So how do you handle averages of groups? Well, everything's the same, except if you're grabbing a group, there's going to be less deviation. There's that's that you got to do a different standard deviation. So for part D, so D is the same online calculation, except what? The standard deviation becomes that new number, 0.2466, that we got right there. Because now this is X bar group average. That's the difference. That's why they set us up with that in the beginning. They're saying, okay, X is for one city, X bar is for a group of cities. In that case, you have less deviation. Can you picture that? Can you feel it? Yeah, let me give you a little bit of a feel. If I was to say, hey, I'm going to grab one person, take our whole class. I was going to grab one person and say, okay, what's their score on the next, what was their score in the last exam? Okay, and then another person, another person, another person. I'm going to get, some highs and lows. The numbers are going to, some people that were getting A's, and the numbers are going to be jumping all over the place, and there'd be a lot of deviation, right? But if I was to say, no, I'm going to grab 37 people and take the average of 37, and then I'm going to grab a different 37 and take their average. Well, when you're taking an average of 37, the highs and lows are going to balance each other out. There's not going to be much change from one group of 37 to another group of 37's average, right? There's less standard deviation. That's why the standard deviation changes. Okay. So anyway, so what does that mean I do? I just go to the online calculator, do the same thing I did before, but I put in a different standard deviation. Let me show you. Let us go there. So here we go. Everything's the same, except right here. Got to get rid of this P. Standard deviation. In fact, I'm going to type it in right here. Whoops. I don't know why I did that. Divided by, oh, no, you can't. Yeah. I was going to put in the new number. What was it? 0.2466. 0.2466. There's the new standard deviation. Calculate 0.9994. That's a lot higher, huh? That's a lot. There's 9994. There's almost 100% chance, 99% chance that if you take 37 cities, that the average amount of pollutants for 37 cities will be in the safe zone, 10.3 or below. So there's the answer to that. All right, let's go back. Okay, so we can see that answer right here. 0.9994. We got it correct. Okay, now, a couple more parts here. For part D, that part we just did about the group average, is the assumption that the distribution is normal necessary? Is it necessary? Right? Do we have to be told, hey, it's a bell curve, right? Because whenever we go to the calculator, and we choose the normal distribution, number 8, the normal distribution, that assumes that the data is spread out in a bell curve. Not everything in life is normally distributed. Most things are. That's why we call it normally distributed. It's what normally happens. But not everything in life is normally distributed. Some things are not normally distributed. So we can't be using the normal distribution calculator if we don't know the stuff is normally distributed. Bell curve is how it spreads out. Except there's an exception to that. In fact, let me show it to you back again. We just keep switching back and forth here. I want to show you the notes. See the notes down here? Note right here. Online, normal probability calculator, note. When n is less than 30, the number, n is the number in our group, right? We're doing 37 cities, right? So we're actually greater than 30, but let's just read the whole thing. When you're grabbing a group and you're asking about the average pollutants or whatever you're studying for a group of 30, less than 30 cities, we must be told the data is normally distributed to use these formulas. But when it is greater than 30, like ours is, we have 37 cities in our group, it will automatically make a normal curve. So we do not need to be told this. Is that making sense? If n is less than 30, you've got to be told it's normally distributed. When it's greater than 30, it will automatically make it bell curve. That's kind of that's an important result in statistics. When you have more than 30, now, by the way, you might say, well, Mr. What about to equal to 30? Don't worry about that. This is all just about, nobody's going to give you exactly 30. I mean, it's just kind of rule of thumb. So don't be nervous about that. So basically, when you have more than 30, it makes everything bell curve. The averages of groups more than 30 are automatically bell curve. So we go back to the question then, back and forth here. Then here we are. RN, let me change my thing here. RN is 37, right? 37 cities. 37 cities. That's more than 30. That's more than 30. So is it necessary? So no, we do not need to be told or assume it's normal. It's a normal bell curve. We do not need to be told that. It'll automatically make it a bell curve. If n is greater than 30, averages of groups greater than 30 are automatically made into a bell. Now, if n is less than 30, then you need to be told that. So is the assumption necessary? No, it's not, because our number is bigger than 30. All right, finally, part F. Find the IQR. Notice what it is. It's for the average of 37. So you have to pay close attention now, and you will on the second exam, to anytime they're asking you about a normal question, all the stuff we've learned about doing normal questions for the normal probability calculator, you have to now pay attention. Is it one city or is it a group of cities? Is it one person or a group of people? Is it one test result or a group of tests? Is it one or a group? So on F here, it's the average of 31 cities. So, okay, so let's see part F. So you know how this works. So let's come down here, draw the bell. And we'll put the middle on there. The average, what is the average? 9.5. It's the average amount of pollutants. 9.5. Okay. And then we're going to go to the online calculator. And it's saying, oh, they want Q1 and stuff. Okay. So Q1 is going to be about right here. And Q3 about right there. You know how Q1 and Q3 work, right? That means this is 25%. This is 25, this is 25, and this is 25, right? The Q1, Q2, Q3, they break the thing into quarters. So Q1, I'm gonna go from this is the low of negative 6/9 um to this high, which I don't know, and I'll leave it blank and go to the calculator and find it. Let's go do that. The notes tell you right here. Um, when they give you a percentile or quartile or bottom percent or probability. So we have a quartile. The low is the negative 6/9. The high is blank. Now watch this. If n is greater than 1, it is. We're doing average of 37 cities. More than 1. Then the standard deviation is divided by the square root of n. Yeah, we got to use that new standard deviation. And p is the probability given. So we go to the calculator and we go, okay. So low is negative 5/9. The high is blank. The mean time of the standard deviation, got the new standard deviations already in there. The p, though, is 0.25 because I'm doing the first quarter. Calculate. So there is the high, 9.337. Awesome. So I'm going to get Q3 now also. To get Q3, it's the same thing. Just erase. So there's that answer. You can check it. It's the right answer. There, that's your answer for Q1. There's your Q1 answer. 9.337 or 333.7. Okay. And now change this to 0.75 and hit calculate. Boom. And there's the Q3 answer. 9.6663 right here. That's correct. So we got the Q1, we got the Q3. So again, you go from negative, so it goes from negative infinity up to that point. That looks like 3/4 of the curve, doesn't it? But you notice we had to use the new standard deviation. That's the standard deviation for a group, not for one, because they're asking me for a group now. And that's how we get those two answers. And we're about done. And then, so, yep, so there they are. Here's this answer and this answer. They're correct. Last one, IQR, you know how to get that, right? You just take the Q3 answer, you subtract the Q1 answer, this minus this, and we're done. And so there we go.